The past couple semesters of these digital electronics classes, we've been learning the basics about digital electronics and the fundamentals. And we were tasked with the way of applying this knowledge. And Adam and I decided to create a slot machine with an FPGA board and the Quarter software. Our slot machine had to find a way to make an almost random number generator. We had to make it display the numbers somehow with a 7-segment display. And we had to make sure the machine could stop on individual numbers corresponding to what the RNG the random number generator had come up with, and then find a way to recognize a win or loss condition on the slot machine.
In order to solve the problem of random number generation, we implemented the FPGA's clock. We divided down a 32 kilohertz clock and connected it with two up counters, 74 LS90 and a 74 LS192 that counts down. We connected the output of our three counters to the 7-segment displays, and we learned that this particular chip's output had to be inverted, or a parsley as we called it, in order to properly display numbers.
Otherwise, it would display exactly what you didn't want to see.
All the inverted characters on the 7-segment display.
And we wanted our 7-segment displays to correspond with we wanted to be able to stop the clock and stop the spinning of the 7-segment displays with the push button on the FPGA. At first, we figured out that we could stop the clock and we could stop on a certain number, but we would have to hold it, and it wouldn't remember what number we pressed unless we were holding down the push button. So we added the clock signal. 1 second. We added the push button with the 32 hertz clock that we divided down there, and tied that to the clock of a JK flip-flop. And if the flip-flop functioned as a toggle, since both the J and the K signals were tied high, so it would function as a toggle. So if you push the button, it would toggle instead of going higher or low. So the end product was a push button that would stop the clock from counting as soon as the button was pressed, and it would display the last number the counter had output.
We also wanted the machine to recognize if the random number generator had stopped on 3 of the same digits, and that would signify a win condition. And then if the 3 digits didn't match, it signified a lose condition. So to solve this problem, we added 2 4-bit comparators, here and here. They compared the outputs of the first 2 with the outputs of the second and third, and then all those outputs drove the red and green LEDs, signifying win versus loss.
And as you can see, this is what it would look like if it was spinning. You obviously can't see that it is spinning. It's a picture. If you have all 3 matching numbers, all of the green LEDs on the board will light up, and if none of them match, then all of the red LEDs will match up.
Here's a legend of our board. A spin button. Each of these 3 correlate to those 3 reels, and then the green and red LEDs for win-loss.
There were a few things that we had an idea for that we wanted to implement, but we didn't have the time or the required knowledge to implement it properly. I wanted to make it so as you started up the the board, it would maybe display like spin or slot and the four 7-segment displays. That turned out to be a little more involved than I had expected. We wanted to implement a way to prevent cheating. Currently, you're able to keep pressing the same button until you get whatever you want, really. And we wanted to change the way that, make it so that wasn't possible. And then we wanted, it would have been nice to improve the interface so it would be less, it would look nicer.
In conclusion, what we started out to do was develop a slot machine based off of the FPGA software, or the Corda software in the FPGA board, that could randomly generate numbers, display them, and match them, and detect whether or not you win or lose.
You can see.
Oh, you lost.
Lost the bass.
See, and that button will start the whole spinning process again as it stops, and that one will stop this one. You got 276. That's a loss. Yep.
How do you cheat it?
You can start and stop each individual reel.
As you please. So he could have.
So you can spam the buttons.
Until you get a jackpot.
Yeah. There we are. 888.
Winner, winner, chicken dinner.
So just don't do that.
Right.
You get a slap on the wrist. So yeah, that's our slot machine. Do we have any questions? Chris, you look like you have a question here. Okay. Yeah, Robert.
Make it where you just have it start and then it would just generate random numbers for a set amount of time, and then just basically choose what random numbers it's on rather than having to press all 3 buttons to stop them all.
Implementing additional logic functions.
Yeah, that works.
Yeah. Or writing a Verilog code that would be a lot more involved than what we learned in Verilog. Robbie, you had a question?
What was the most difficult part?
Really probably getting the, well, what do you think?
Getting the somewhat random display of numbers, probably.
Yeah, we had to divide the clock many times, and
Yeah, we had to divide the clock signal 4 times, and then we ran 2/3 of the signal through up counters and 1/3 of them through a down counter. So
So what is your clock running at?
32 hertz.
Well, but I mean, when you after you divided it down.
Sorry, what?
After you divided it down.
Well, it started off at 50 megahertz, and it divided to 1 megahertz, and then divided that by 32, 3 times down to 32 hertz. So its current speed is at 32, so you can see it.
that way, it actually just displays slow enough that you can read it cycling through the numbers.
Yep.
But it still doesn't match the frame rate of the
Somewhat, you can tell a little bit, but
right.
So is it some of one of the 3 digits? Are they all counting up, or are they all counting down, or is one of the reels?
The two outside reels count up, and the
Okay.
middle reel counts down.
And that happens at the same clock frequency.
yes.
Yes.
Okay.
Yep. Also, if we can bring the diagram back up, this whole section, that was kind of hard. Making it display the
Red and green LEDs.
red and green LEDs. It was a pretty simple fix, but we really had to bang our head against it for a while. This here is all of the push button signals ORed with the 4th button that starts all of them again. And
The spin input.
yes. And am I looking at the wrong thing?
No, that's right.
Right, okay. And those come from the JK flip-flops, I believe.
Yep.
And we had to order those together and then
Invert them.
invert them.
And those with the comparator
Right.
outputs.
Right. And that would be able to detect if all the buttons had stopped on the same number or if they had stopped on different numbers, giving you green or red when lost. So really the clocks and then the wind condition was probably the hardest parts, but they're about equal in difficulty, I'd say.
Getting to detect all three similar.
Mm-hmm.
binary.
Yep.
Any more questions?
All right, good job.
Thank you, gentlemen.
Thank you.
Can I have a second group? A digital analog converter. A simpler form, more of a basic form of DAC that is, it implements pulse width modulation, PWM, which is a nice, cheap, affordable way of using a digital input to get a nice, steady DC analog output out of the other end of it. So I figured that would be the project we'd want to try to do. It definitely incorporates elements from both of our classes. I say both of our classes. We're not all in circuits, I guess, but there's a lot of analog on the other side, which becomes very crucial. So I didn't want this necessarily to become all about the analog filter circuit on the end of this, because this is our digital class. But the way the two work together is really very interesting, and I think the project worked out really well, and we should all be able to learn some good stuff from this. So I started out with a 4-bit design, which I don't think I have. I didn't take a picture of the 4-bit schematic. What you're looking at here, this is right after I scaled it up from 4 bits. We started off, do we have a little bit of focus? Or am I
That's the best focus I can get. There is no focus.
I've got, I think we used the same counter as you. That was a 7490, I think. 4-bit counter. So I started off with just a 4-bit counter and then a 4-bit comparator. And I got that working to achieve our PWM output. Happens right here. These are the human inputs, scaled up to 8 bits. It's coming from the same 50 megahertz clock. We did divide it down. Initially, I started down at the 32.768 kilohertz that you guys were using back there for the design, and I'll get into why that clock speed had to change. But I wound up, there's such a vast parts catalog out there when it comes to selecting these digital components. After I had my 4-bit stuff, and I decided just to double it and use multiples of them to get to our 8-bit system, rather than hunting through and find the exact equivalent version in an 8-bit chip. So I just plopped a couple more down there. These counters work. The output of our highest bit here feeds the clock into this. So this becomes our 8-bit counter. These are actually have another feature so to make them just a binary counter, you have to tie in the A output, the least significant bit output, into what they call the B clock input, and that makes it count just as a normal binary counter. So we've got our inputs here, which are coming in this case on our Cordis board, which we should probably get set up and maybe programmed so we can show off this thing. Our switch inputs are coming off the Altera board. And as what we've got set up now, you're inputting a binary value. And that's going to give us, at the end of all of this, a voltage, hopefully a clean DC voltage of a desired state. It's going to be 0 to 5 volts adjustable range is the system scale size. So 0 to 5 volts, we should be able to give you a nice clean output. We need another board. Probably a good time for an intermission or something. Huh?
What kind of board?
We need one of these.
You can use that.
What do you say?
Can we just use that one? Okay.
I don't think we can program it up here.
Oh, that's right.
You can program it from here if you have the phone.
Go around and program
Chris, I
it.
remember that you took several pictures of the
Mhm.
board actually working. Yes, that
Mhm.
probably is enough to get your point across.
Okay. Well, we can see what the pictures look like. This, I wanted to leave that on there. That was my messy. This is the cleaned up version. This is, if you're going to present work to Cliff, don't make it so much like this. Make it a little more like that. Keep the instructor happy. Okay, so here's our 8 bits of input. There's 4 there and 4 there. It's really relatively simple. Most of us in this class of what we've got going on, it's just a couple counters comparing the output of the counters to our inputs. I liked these comparators because it gives us 3. It gives us a low, an equal, and a high output. Which, okay, now I'm losing my thought. The PWM coming out here, for example, if we wanted, let's say, half voltage level out of this, 50%, we're going to turn it halfway up. Whether it's a light bulb, whether we're driving a light bulb or a motor, we want half speed, we want half brightness. That means the output coming out here will be high half the time and low half the time. That's what's providing our duty cycle that's going to our analog filter, which I think is the next picture. The next circuit we have,
You want to see it?
this one
Okay,
here. It's an RC circuit, which we've been getting familiar with in analog class. Right here is the whole digital circuit from the other. And this is providing that pulsing 0 or 5 volts into this. And because of the analog properties of the interaction between our capacitor and our resistor, that is going to smooth it out into a constant DC voltage. Let's step to one of these other pictures. Let's see, keep going, I'll show some early. Okay, go back up, won't show those yet. This is an example, kind of overall, one of these two. The red lines, which you can't see the full scale of in this because I'm zoomed in to show this, but that's the output from the comparators going 5 high, going 0, 5, 0, 5 at our clock speed. And this line here is the reaction of that 0 and 5 volts between the resistor and capacitor. Attempting to turn into a DC voltage is what you see. There's a lot of noise right now. There's way too much. So this was one of the first values I had tried. The key to this design is getting this noise below the step size of our DAC. So if we're working at our 5 volt scale with a 8-bit DAC, that gives of step size means our DAC has the resolution of about 19 millivolts. 19.6 millivolts, I think, is what my calculations were showing. So in the real world, it's pretty useless to design a system where you can decide in steps of 19 millivolts what voltage you want out. But if you're getting noise that's bigger than 19 millivolts varying, you've got a useless device. You're within several steps of range. So the key to the design was getting that noise down below. My design objective was to get below 19 millivolts. 19.6 was acceptable. So if I got below 19 millivolts of noise variation there, I would consider that excess and be able to say that the DAC is accurately putting out a known voltage within its range. I think maybe the next slide shows it maybe getting smoother. What this is, ignore the blue line at the top. This is a bigger scale drawing. This is our 0.5 from our comparator. This shows you the relative scale of what the DC does in fact look like compared to the 0.5 all over the place. It's pretty clean, it's pretty straight, and at this point you can see how it's leveled off into a straight DC voltage. The other challenge of building this, there was a lot of time spent playing with the resistor and the capacitor values, which being in digital class, I didn't want to devote a lot of time to that, but it was essential to at least get it narrowed down within the ballpark to start getting it to look smoother. The consequence and the compromise that had to be made as well, as whenever you're increasing, as it turns out in this circuit, when you're increasing the value of the resistor, it starts to smooth the voltage off because the larger resistor slows down the current and gives it, and it's not going to change as fast between our pulses. The compromise to that is it's going to take, if we start off, can you go back to that first, that one.
No?
We're starting off at 0 here. System start, you can see in this example how long it takes to achieve our desired voltage. Depending on the application of what you're trying to control the voltage of, that may or may not be acceptable. Some things you have time to wait. Other things you need an instant reaction. So I kind of, looking at this was probably going to be something simpler like a motor speed control or maybe like a light dimmer. I gave a design goal of 0.6 seconds to reach desired voltage output. This graph is showing, again, we're at our 50% voltage request of we've got the knob turned up halfway essentially. So 50, if this is 5, here's our 2.5. You can see it takes about 0.6 seconds is happening right out in here. I felt that was about the limit for what I wanted to see. I didn't want it to take 5 seconds for the voltage to get to where you wanted it. And that's probably a little annoying no matter what device you're trying to power off of it. But it does give, by compromising there, you do get a much smoother voltage. Now through all of this, I still was having a problem getting that noise down within my 19 millivolt requirement. As it turns out then, looking into other parts of the circuit, the easiest way, I felt, at least within the means of what we had covered in class, I had gotten it as close as I possibly could using the resistor and capacitor values. What else can we change in the circuit? I had to step back and increase the clock speed. I just started by doubling it. Because as it turns out then, it also has the effect of reducing noise, because when you double the clock speed, or you increase the clock speed, obviously your pulses get much closer together. There's much less time in between those pulses. There's much less time in between the pulses, that noise has much less time to rise or fall. And that was very crucial. And if there's no limitations on the clock speed, we could get that noise to a very low level. We can have a very clean DC output as long as clock speed there isn't an upper limit on it. So I wound up, final clock speed for this, of what we're looking at, turned out to be 262,000 hertz. I doubled it up a couple times from where we started. And what we're looking at here, I think we can probably start, this is all done in the QUCS simulator. I think we can look at some O-scope shots now. I think, yes, these are all final version output shots here. That shot there is at almost max power. This is 2 channels on our oscilloscope. This is the output from the comparators we're looking at, and this is the DC output that we're shown. They're not using the same 0 lines, they're separated, but just for a scale of noise of what we're seeing, here's our high pulse, here's our low pulse, a short duration low. So I would say, I forget exactly what duty cycle I was at, but this is probably around 80% duty cycle. And you can see it's putting out a pretty clean noise line on there. There is some much smaller deviation. If I had better focus and on the O-scope, you can see the smaller minute amounts of noise going in there. But if you step back to the other picture, this is what I was considering our worst case. At our half power level, I looked at my noise at around 50% output level for most of my design work, because that is the worst case scenario when it comes to noise for this. You're spending as much time on as you are off. That's giving it the most amount of time possible that it could rise and fall to create this noise. So this is our final design, 50% cycle. I've got the noise scaled, I'm zoomed in pretty far here. That turns out to be right around 19-20 millivolts of noise, which is about as close as I could get it. There is some evidence of that the noise technically does exceed that for micro and nanoseconds at a time. It does spend most of its cycle well within that range, so I thought that was fairly successful. And it also dawned on me, I guess, well, Cliff helped explain to me that maybe you can't always just go infinitely high with the clock speed. There might be reasons to not do that. Because of radio noise, we know these low voltage digital circuits can be pretty susceptible to noise. So we might not want to go just crazy with clock speed. In this particular application, and if what you're building doesn't need like many steps of controllability or resolution of control, like in this case we've got 8 bits of control on a 5-bit system. That's 19 millivolts of step size. If we don't need that fine of control, in this case, we could step back to a 4-bit system, and just using the 4-bit counter with the same clock speed, we would essentially be having these, because we only have to count halfway up through 4 bits now as opposed through the 8. That would have the same effect as increasing the clock speed. And so that would be another way, if you can sacrifice the resolution, we could get a cleaner output by stepping back to 4 bits. But we kept it in 8-bit here because it was a good exercise. And the 8 bits of control, 19 millivolts, might seem a bit extreme in step size. Like, why do we need that fine of control? Well, this is our raw output's 5 volts here. That output can be taken and amplified to run all kinds of motors or arrays of light systems or whatever. So once it's amplified, now the resolution might actually be useful. When you're controlling a broader range, it's good just to have the control there. So that benefit would be realized after some form of amplification past our 5 volts. Another challenge that this is probably extremely picky, and in the application of this particular device is completely useless, but just using the comparator of the higher than output from the comparator, I realized it wouldn't be possible to get a technically true 100% full on output from the comparators, giving what you could call actual full output from the whole system. With these comparators, I thought it was handy because it had the 3 outputs. So by tying in essentially with an OR, I think if you go back to this one, so back over here, I just OR'd the A less than B output with the equals output. So when we are at max, we set all these to high. We've got 8 ones coming in, max 8-bit input. That means this actually can stay high 100% of the duty cycle out here. So it enabled the whole system to actually give its possible max. Now the way this system works with the RC filter side here, the actual voltage can be trimmed up or down to some preference with the potentiometer on here. So we're working more or less at 5 volts. We're a couple tenths over, I think, right now at max. But that just gave it freedom in design with the potentiometer there. That's the reason of doing that. So why do all this? Just for this complicated light dimmer. If you're just building one and power consumption isn't really a big problem, then I wouldn't suggest doing this. I would just go get a light dimmer and waste that extra electricity as heat when you don't want your light that bright. But the upside to doing this is if you've got to save power, this digital circuit will do it more efficiently than a big power wasting potentiometer or rheostat in your circuit. That can add up in larger scale applications and in machines. I think that's about all I have. That brings us kind of from the start to the end in this project. You have anything you'd like to add? Anybody have any questions?
Was harder, making the circuit or on Quartus or making the circuit on your breadboard?
The challenge for me definitely was the analog side of it with the QUCS simulation and then putting it on the breadboard. As you can see, there's not a whole lot going on digitally here. But the interesting part is the way this digital interacts because of the clock speed and the behavior of those comparators, the way it interacts with the analog side, I thought was very interesting. So both aspects were really very relevant to the project. I got lucky, maybe it was luck. All the work on the simulator that I was predicting with QUCS, once I got it on the oscilloscope and measured the performance of the thing in real life, it matched up and it was reasonably accurate. All these, I guess it might be good to note that all these calculations, all this, go back to one of those noise simulator shots, yeah, like that. All of this could have been calculated by hand using the transient analysis that we did learn in circuits. Way too time consuming to do that, especially when we're in a digital class. To do that many analog calculations, it would have been prohibitive. And also, simply, just from that aspect, it would have been way too much time. But to actually calculate it through the full scale from 0 till ramp up time is achieved would have taken an enormous amount of calculations. Because as you can see, If you go back to the ramp overall bigger one, yeah. There's noise happening the whole time. So depending on how I randomly decided to start doing these calculations by hand, I can see what the voltage is at what time on charge or discharge, and I would see it going up or down. But it would take many, many calculations, thousands and thousands and millions, to actually see that over time I'm actually increasing and my number is going up, even though side-by-side calculations for this cycle and then the very next cycle might show a down, but the overall pattern is up. So that would have been very confusing to see and interpret doing it by hand. Stuff like this is very essential. It lets you play with it essentially and get an intuitive feel for how changing parts of the circuit affects other parts, so you can see how this graph comes to be. Personally, I think for most DC things I'd like to power, this is still too noisy. But for most general purpose devices, I think it would suffice. So I think it was a success to that end.
Do you have any more plans to carry this on into audio applications, since that's a large portion of your interest?
I wish I could say plans. The plan is to find a plan to, yes. Now that I'm starting to actually get my hands on and see how these DACs perform, that's a big interest of mine in the audio field. It's fascinating, and it seems fairly simple, but I think it has been for the past few years, and I think for the next few years also, there will be big innovations in the market in the DAC side of the audio chain. It's cost effective to do, and they're figuring out how to create very high performing products that are affordable. And that right there is going to guarantee that's going to be a popular product when they can keep improving it, and you don't have to charge someone $10,000 for this top of the line product. It's really, yeah, it's cost effective. So learning how to better and better implement it at this low budget level is very interesting to me. After seeing the benefits and hearing some of the benefits that a good DAC can do, it's interesting technology. So yeah, I'd love to be able to take it that direction. So thank you very much for your time.
Well, obviously, these are our objectives. Like, we had to create a commercial clock, old standard, that would, like, portray it in the typical, like, hours, like, minute, and how we set the clock was we ran a faster clock through it, so the numbers just kind of cycle up at a faster rate, and you kind of stop them approximately where you want them.
From choosing to design the clock program from Chorus, since we had experience of basically programming other past projects in the Chorus program, we decided, or we felt comfortable actually designing within Chorus is what I'm trying to say. But to help basically make a smaller situation, if anything were to happen with any part of our project, we decided to segment our clock program into basically key main parts. Basically being the clock pulse that once divided would power our seconds, which our seconds program, once that was programmed, would basically feed into our minutes program, which once that was programmed right, would feed into our hours program. And once all those parts were made separate from each other to basically eliminate more errors that could have happened. But once all of those were proved to function correctly, we added in basically our two sub-functions, which were basically the clock adjustment time, which we were starting to run short on time for doing, but it basically just sped up the clock until the desired time where we turned it back off again. Then was our AM PM light, which just toggles from one light to the other. That really just took about 10 minutes or less. That was really easy to do. But those were our sub-programs.
Okay, we got snippets. Basically, you can see here that our instructor provided us with these two things, and it outputted our 32 kilohertz signal. And what we figured out was 1 hertz equals a second, so we had to figure out how to divide this down to 1 hertz, and it was easy because 2 to the power of 15 is exactly the starting frequency of 32 kilohertz. So we ran that through these things.
Didn't count.
I will get back to this. This is a multiplexer. We were go back. Okay, it was ran through this, and basically this was 2 to the power 8. This was 2 to the power of 7. Adds to 2 to the power of 15, so it gave us the frequency that we wanted.
Oh, yes. Well, going forward from that, after we had actually made our clock pulse reliable to where it was outputting a 1 second signal, we actually realized that after it was divided by, or outputting our 1 second pulse, we were able to actually add in our multiplexer, which we could cover after I mentioned, but basically the output signal itself was just tied to how I explain it, a B segment driver to where it outputs, how do I say, it was outputting the binary of basically 1 up to 9, and it was keeping track of that in the BCD segment driver, which is basically what you would see here as our 1 value here, which it would go up to 9, and then clear going back into our 1 second pulse driver, and then basically pulse the second tens place of the decimal for our seconds forward 1 up to 60, where it would roll back over to 0, but then sending a clear signal to clear basically the seconds driver itself, as well as sending that signal to power our minutes forward 1 minute.
So this is basically like the signal that comes from this guy right here, 2QC, and once that comes through, this is a dual 4-bit counter. I don't know if I can get it. So we tied the outputs into it, allowing it to share the same, gosh dang it. Okay. Well, basically, this counts originally to 99, which you don't want because you want your seconds to count to 60, hopefully. So we had to clear it at 60, and that's what this NAND gate does. It emits the clear signal, and as soon as it clears at 60, you want it to give a minute over. So the same clear signal, which is active low, needs to be inverted to be a 1, which is the same time as we need our minutes to be. And that comes in right here. And the minutes and the seconds are wired up identically. Like, the only difference is this frequency right here is run off of like 60 seconds, and the seconds frequency is just 1 hertz. Still got the same setup leading to our 7-segment drivers.
Well, basically, the numbers coming up from, I can just, if you guys can see the mouse, it's basically running from, this inverts the signal coming from basically reading our multiplexer, just reading the numbers that's going into it, such as, we wanted the clock to roll over at 60, as I was mentioning, and basically our NAND gate was reading when a 6 was present through binary, and was sending that clear signal to clear our minutes. But it's essentially just the representation of the 60, or 6 anyways, which was the key part, was this was a 1 signal inverted to make it 0. These two middle signals were both 1 still, and then the last signal was inverted to make it 0 as well, therefore equal 6 to be, then once all of that was met, it was then sent to the NAND to then send a clear signal.
Now, it should probably be noted that these 4 outputs go to the right 7-segment driver, and then the 2Q outputs go to the left 7-segment driver as most significant and least significant. Now the hours are a bit funny. Not like haha funny.
Getting it to function.
This is still the same counter we've been using for the minutes and seconds. We got some more stuff back here, but this would also count to 99. Can't have that, but we don't want it to count to 60 this time because you only want your hours to display up to 12. So this at most would display a 2, and this at most would display a 1, being the leftmost 7-segment driver. The hardest part about the clock, in my opinion, was getting it, when it cleared from 12, it would go to 0 naturally, and you don't want that. You want it to go to 1 o'clock. And that was a very tricky part to try to get it to clock at one additional time. When it cleared, it was just having all sorts of timing issues. Basically, how we managed to trudge through it, I think we might have overkilled it, but it worked to a point. We detect the 0 state here, and this is our clear condition. The problem is it's got to clear first, then it has to do an additional 1, or otherwise you kind of get the ghost in the machine effect. You don't really, it's not reliable. I don't know if you could.
In short, we have the clear signal present that basically will condense the signal into the NAND gate that is held longer by our present mouse. And the wire up here, if you can see the mouse, is basically to the 8th power, which is part of basically a feed wire we had from one of our divisions to make originally the seconds pulse. We used that to be ANDed to our clear signal. That way it would hold the signal long enough to actually do its function. As we encountered with this program itself, every time we try to add this to everything else that had been tested by itself and later added together, they all worked fine, but every time we add the hours in, we were having a odd issue of Quartus, or just not registering our value signals that were coming in, which is quite literally why, before we had actually added in our function to make it go to 1 o'clock, is why our D flip-flop is actually right here, because literally it was Quartus actually running a subprogram that was preventing us from actually having our clear signal on long enough to clear the function at all. So it was actually going to 99 even though it was programmed to go just to 0 after reaching 12. And going from that point, we suspect that there may be an issue like that of just the signal for going to 1 o'clock is not being registered long enough, or it's just a subprogram in Quartus again that's causing an issue. Either way, it's a simple fix. We just need the chance to do it.
Given more time, it shouldn't be too hard to fix the problem. When we had a push button here for our 1 o'clock one for the hours, because you don't want to wait 60 minutes just to see if your thing works, it worked fine with the push button. We could push it and it cycled over, then went to 1. But for some reason, when we tried to hook it to the minute output that would lead into the hours, it did all sorts of funky things and counting to 99 or clearing to 2, and for no adherent reason. Good way that we resolved it though is theoretically, since this detects the 0 state, that leads into this AND gate. This multiplexer, the VCC is hooked up to B, so when B is active, it'll give an additional 1. So when it clears, it selects B. B goes through here, gets as a 1 with this OR, and then this comes from, I believe that's our minute, no. Yeah, this comes from the system clock, I believe. And when it clears, originally the A, which is our normal clock, would be a 0, so it would go to 0 o'clock. But since we hooked this up, when it clears, the B gets outputted as a 1, so it clocks again. And it worked until we wired it up according to how it should be, and then it didn't. But given more time, we could definitely fix it, and if you'd like, we could hook the board up and show you if it wants to be nice or mean.
It basically looks like a very slow version of the slot machine if you from the prior
Doesn't roll
project.
backwards, but
But yes. From summary, our group basically created every part of the project successfully, segmented wise. We made it tested by basically hooking up push buttons to every portion of it and LEDs to basically see if the output was high or low at various parts of every segment of the part. And going from there, it just
one thing that was very trivial that just has to come with the standard clock is our AM PM switch. Comes from a JK flip-flop, which is always in toggle mode. So one of these is the AM or PM. Just got to designate one, but every 12-hour cycle it'll toggle to this or toggle to this. So that allows that to let you know if it's 2 p.m. or 2 a.m.
Basically, in closing, we made every part of the clock successfully. We understand one way to not make a clock completely work, but we understand how the clock can be repaired relatively fast. And going forth, the clock would actually be quite reliable given the time to fix it.
There's just a lot of timing issues that we had fixed some with D flip-flops, just to add small delays. If we had more time, I imagine we could fix a lot of the same timing issues with more D flip-flops, but it would just take a little debugging. It's not a serious problem, but it's definitely not ready for like manufacture.
So you did have a full working version that was working manually?
Yeah,
Yes.
worked manually until you hooked the minutes into the one clock of the hours, and then it just didn't. There was some timing issue. It was doing other stuff before other stuff for some reason.
We had that issue come up in the past where basically our clear function for the hours, it was basically designed the exact same as the minutes and seconds were to basically send the clear signal. But for the hours alone, we weren't actually getting the clear signal when it was hooked up just like any of the others, and it wasn't doing the clear signal mainly because, as we found out, there was a subprogram within Quarters that basically was doing some odd calculation
It's like an
outside of our
optimization
program,
error.
but it was yes. Which we suspect may be the issue of basically why our clock is going to 0 hours instead of 1 o'clock as it should, which it did outside of any effect on any part of the program being hooked to it.
But I mean, we're pretty certain our counter is a ripple counter too, so it like has like propagation delays between it, and that did cause problems. That in specific we fixed because like that was its own timing issue, not like a Quartus optimization thing or whatever, but the ripple effect was causing it to like jump from like 10 to like 13, which would cause it to clear to like 11, and it was just doing all sorts of weird things. The timing's off. A lot of stuff is in sync, like with like the system clock and stuff, and they run at the same frequencies. We used a lot of the same parts. There's just some timing error in there that needs debugging, but it's an overall successful project, and I think I learned a lot from it.
Any questions? Thank you.
Well, thanks everybody. I think the presentations were good. Certainly your projects turned out well, so I think it was a great exercise, and I'm glad that you guys persevered. I know that there were, I mean, it's part of the experience, right, to have to beat your head against it for a while. I think everybody experienced it, but you came through it, so good job there. If you will, please send me your slides, so we'll incorporate them in these presentations. If for whatever reason you don't want your presentation used as a part of the Facebook page or the website or promotional materials, and let me know. Otherwise, I'd certainly appreciate it, because we'd like to build up interest in the program and get the word out there of what we do and maybe get some more enrollment.